So here at this stage, at the 119th minute, my double bus bar protection is operating and it's stripping all my 220 kV breakers which are connected to the bus. That is my assumption. I'm not saying it just happen every time. It's my worst assumption, as we discussed it before. And the next minute, so I thought it's a normal fault or temporary fault, whatever it may be. I cleared the fault and I am just closing all the breakers again. And in the next, again, it's continuous. And finally, I brought again this load at the end of the case. It's a kind of a reliable thing. It's totally your assumption thing. I cannot say that this is a standard. It totally depends upon your project. So when we got this, so now you are preparing the load cycle. You can see the load cycle. This is the continuous. Continuous will be there here. So this one is the tripping one. This one up to here is the closing one. Yeah, wait a minute. I want to draw a line here. This whole part is a continuous one. And this graph, this part is a tripping of the breakers with the double bus bar. So the same weight you can see on this column also. Here I'm just closing the breakers. Okay. So this is my assumption. Or else you can shift this across all these spans. Now you can draw like this, continuous. I want to bring this to the top here, first, second, and last. You can do, or else you can also do the first, second, and again in the middle, and again in the last. You can. But when you're developing this, think about that. Will it happen? What is the probability to happen? So you have to think in that context too. So when you're done with this, then we have to, we left with the load calculation where we can see here, this is my continuous loads. This is the momentary load of my 220 kV panel. And I'm calculating the current here. And in the first period, what is the current? 1.28. And so on. So in the first period, the current is, in the battery, the load is current in, because the battery's capacity, we will call in the ampere hours, number of amps per hour. So during this period, the battery has supposed to pump or give 18.6 amps. And in the next period, 119 to 120 period, here you can find some momentary loads. What is the momentary load? 0.12 for double bus bar protection. Okay. And closing breaker tripping, 10.76. Sorry, 27.49. So the momentary load is this plus 18.6 gives you 46.21. And in the third step, where I'm just closing the breakers, there is no operation of any relay, but I'm just closing the breakers. 21 number of the breakers I'm closing. Why 21? In the 220 kV, before I said that 220 kV are individually pole operated. Right? So 21. 7 breakers, 7 into 3 phases, 21. So at this stage, at the third period, what is the load? 32.34. And in the fourth period, again, I required 18.6. And again, fifth period, it was assumed that the operation of double bus bar protection again. So that results to 46.21, where you can, we got the same in the second period too. So when you're done with this, then we are calculating this, we are calculating the battery. Where the first period, 18.6, the battery has to send 18.6 amps of current for a period of 119 minutes. That is my condition. To satisfy this condition, there is a one factor that we would call as a capacity rating factor, where it comes that how many amps that a positive plate supply for a period of time at 25 degrees Celsius. So you can say that it's saying, suppose a 3.06 amps, the positive plate can supply for some period of from time period T. So this 3.06, the time period is 119. So now just I am multiplying this 3.06 factor to the 118.6. So now you got 54 or 56, 56. So I can say that up to this step, suppose up to this step, I can conclude that I require a battery size of 56 Ah. But there is a next period where the battery has to send or has to pump 27.7 amps in the next minute. First 120 minutes, 18.6. In the next minute, 27.7. So for this, the capacity rating factor is this. So if you want to know these values, you can take from the Google, you can Google it also, you can get, or else you can gather this information from the manufacturers, or else you can easily find it in the Google. Otherwise, you can also find this in IEEE 485 too. So just I'm multiplying this one to this. So now my battery back capacity is not 56, it's 71. Now I have to say, if I'm selecting a 71 Ah battery, where it can feed the load of continuous 18.6 for 2 hours, and at the last minute it can also capable to feed 27 amps extra. That is my conclusion. And next, I am looking into the first 3 periods: 18.6, 46.21, and 32.34. 18.6, okay, 119, next minute 121. 46.21 also I'm calculating it too. But I already calculated a 46.21 into 2 times. But actually I required the next minute only 32.34. So I'm just minusing this 32.34 from 46.21, which gives you minus 6.95. So now your battery capacity required is only 67 Ah, not 71 Ah, to satisfy a continuous load of 18.6 for first 121 minutes, and again at 2 loads of 46.21 and 36.34 at the last end. Similarly, doing for the first 4 and 5, finally, it arrived that 94.38 capacity of the battery I required. Again, as said before, this 94.3 now is an uncorrected size. Now I'm just multiplying this with the temperature correction factor, aging factor, and the design margin. So finally, it resulted to what? 162.3 H. So finally, what is the battery H I required? I required a 162.3 H battery. But that battery might not be available in the market. So we are just exploring to the market, and we are just inquiring what is the battery age capacity which nearby to this rating. So I found in the market a 200 Ah battery is the next available rating after this 162.3. So I selected 200 Ah battery. So this is my sizing and selection of my battery battery. So I can conclude that I require a 220 volts 200 Ah battery bank. So when you're done with this battery bank, the next few steps, the sizing of the battery charger, it's very simple. In the battery charger, as I said before in the starting of this sheet, we are having two chargers. One is a float charger, other one is a boost charger. Float charger is the battery. I am using the battery to charge. It's a kind of a tickle charging to make my battery in the charged mode, continuously charging. Right, that is a float charging. So at the float charging, the supply voltage would be 220 volts. You better that. But in the boost mode, the battery has to charge quickly. So we are giving more voltage to that battery from the battery charger. Even though we are giving a more voltage, suppose a 242 volts to the battery, where the battery bank is getting charged. At the same time, the battery charger is giving the same 242 volts to the load, which is not good to do that. So at that boost mode, the process will be the supply, this 242 volts will be directed through some dropping diodes where the voltage will be dropped and the sufficient voltage of 220 volts will be delivered to the loads. And 242 volts will be given to the battery. So there's a mechanism will be there inside the battery charger. So finally, to calculate this charger ratings, what is the charger continuous operating voltage? Continuously, how much to 18.6. Float charging current of the battery equal to 2 milliamps per Ah. So for 0.4 Ah. So I'm just adding up 19, taking 10% margin on this, and finally giving a 22 amps float charger. Coming to the boost charger, just a simple calculation, minimum 12% of the battery H capacity. Battery H is 200 Ah, 12% of this 24. And again, nearest to what is the maximum rating among the FC and FCBC I'm considering, which is 25 amps. So I can select that 25 amps is my FC and FCBC rating. This is my battery charger rating. Simple.